Welcome back to the thermodynamics course. So, in the last class we looked at definitions of the basics of thermodynamics. We looked at what thermodynamics deals with definitions such as state and path and process and so on. So, we will go on to what are called exact and inexact differentials. Okay, so, we looked at essentially the fundamentals in the last class. So, we will now go on to what is called as exact and inexact differentials. These are also called as state and path functions. The exact differentials correspond to state functions and the inexact ones correspond to path functions, and we use different notation to represent them. We look at what this is in a moment, but we look at the notation. So, we use the alphabet D to represent an exact differential. So, for example, we write d phi to represent an exact differential. In contrast, for inexact differentials we use the Greek letter del. So, we write del phi for a inexact differential. In some books this is also written, for example, with a d which is cut. So, it would be written in something of this kind. So, what we will see is that properties are exact differentials and they are only defined at a state. Of course, a state requires that the system is in equilibrium, and once you have a system in equilibrium, the properties only depend on that particular state. And in contrast to that, work and heat interactions are inexact and they depend on the process or the path. It sounds a little abstract at the moment, but we can look at it with the help of, say, something like a map. So, as we discussed earlier, the state is something which depends on the properties, and you can plot any properties on a map. So, for example, over here we have a map of India, a physical map. So, this shows the latitudes and the longitudes. So, if I want to specify what in thermodynamics would be called a state, I can think of it as a location on a map. So, if I want to find out a location where on, say, a pressure temperature diagram would be a pressure of a certain value and a temperature of a certain value, I can think of it as equivalent to looking at a location on a map where, for example, the latitude and longitude are given by a certain value. So, if I, for example, if I take this location here, which is where I am at the moment. So, this has, I can specify this by giving the latitude and longitude, and if I give those values, everybody knows that this is the particular place which it represents. And corresponding to this location, today there is a certain temperature associated with it, there is a certain altitude associated with it, and there is a certain velocity of wind and a lot of other properties associated with it. So, similarly, if I wanted to specify some other location, I could say go to some place which is at a latitude of, say, 28 degrees north, and I could say a longitude of 76 degrees east, and I would get, for example, this location here. And as long as I give the latitude and longitude, everybody knows that this is the particular place we have to go to. Instead of giving these two properties, I could give some other property. For example, I could say go to the place named Hyderabad. Okay. So, the question is that is one attribute of this state enough? So, in this case it may not be enough, because, for example, there is a place called Hyderabad in India which all of us are aware of. There is also a place called Hyderabad in Pakistan. So, I may need to tell you something else. So, if I say go to the place called Hyderabad which is at a latitude of around 20 degrees actually, then I would be able to find out that this place is somewhere over here rather than somewhere in Pakistan. Or similarly, if I say go to a place called Salem which is in Tamil Nadu, if I did not say Tamil Nadu and I just said Salem, then if you Google up for it, you would find out there is a place called Salem in Tamil Nadu. There is also a place called Salem near New York in the US, and you may not know which place it is. So, if I told you the name and one other attribute, for example, I said it is about 12 degrees north, and then you found that the other place is a lot farther to the north, then you may be able to find out the place. So, in this case I may need, for example, two attributes to tell you where to find out so that you can locate that position on a map. Okay. In some cases it may be sufficient to tell you only one property. For example, there are these special places. So, if I say find out Mount Everest, there is only one Mount Everest and that is sufficient. So, in a similar analogy we will find later on that there are certain conditions where if I just tell you one property, that is sufficient to identify a state in the thermodynamic sense. So, the variables we usually use are things like say pressure and temperature and specific volume and so on, and we may need to specify two of them or one of them or more than two of them in order to specify the state. But since we can look at all of these thermodynamic properties as say maps, for example, we can have a pressure versus volume map. So, we can think of all of these as locations on a map. So, if I have a pressure which has a value of a certain value A and a volume of a certain value B, then if I say go to a location which has a pressure of A and a volume of B, you would find this location, which is in this case a distinct location which can be found. So, these are things which we consider as state functions or properties. So, these would be represented as exact differentials, and if I wanted a change in pressure, a small infinitesimal change in pressure, I would represent it for example as dP, or a small infinitesimal change in volume I would represent as say dV and so on. In contrast to these, I could ask other questions. For example, if I go from Chennai, which is here, okay, to let us say I go to Delhi, which is somewhere over here, what is the distance I would travel in order to go from Chennai to Delhi? The distance of course depends on how I go. So, I could take a road which goes somewhere like this, or I could go for example as in a more or less straight line, or maybe I want to do some sightseeing. So, I start from here, I go somewhere else, maybe I go somewhere near Calcutta and then I go like this. So, the distance I travel to go from one point to another would naturally depend on how I go there. So, I could go there in a number of paths, I could go by the shortest possible path, I could go by any number of paths, I could go in this fashion or I could go like this and then decide to go somewhere here and then go. So, in each of these cases the distance which I travel would be different. So, these kind of functions which depend on the path which I take are what are called as path functions. We will see later on that work and heat are two examples of path functions, and these are represented, the differentials are represented as I said earlier by the alphabet del. So, if there was a small part of this path, I would call it for example in the case of work as del W, and we will see later on that we used the alphabet Q to represent heat. So, if I wanted to represent a small quantity of heat which is transferred, I would represent it for example as del Q. So, in the case of the state functions or the properties, we talk of a certain location on the map having a certain value, whereas in the case of path functions we talk of a certain path being followed when going from one location to some other location on the map. So, mathematically we can look at what it denotes on a graph like this. So, if I am for example on a plane of this kind, let us say this is the x axis, this is the y axis and this direction is the z axis. Let us say I wanted the value of altitude or height which is represented by z here at some location which is corresponding to the third point here. So, in this graph what we see is that the slope is constant along this direction, along the x direction, and it is the values along the y direction are not changing at all. So, this we see is a plane where the height is varying as I go along x. As I go along the y direction in this direction, the values on any point, the altitude values are not changing at all. So, this would be essentially a function where we would say that z is a function of only x. So, z varies as we go along the x direction, or the height varies when we go along the x direction, but the height does not vary when we go along the y direction. So, this is what we would say, and if we were to look at small changes if we go along x, or in this case because the slope is constant, this is, if I take any of these over here, this is a straight line. So, the slope is constant. So, in this case, if I wanted to know what is the altitude at any point, which is, or if I wanted to know the change in altitude between some point and the ground, so change between this point and the ground, so that will, I can call this as, for example, as dz. And the way I would find this out is find the slope of this line or this plane, which is essentially dz by dx, and multiply it by the distance I am, which is essentially dx. So, this would tell me what is the dz, which is in this case, for example, it appears to be about 6, and dz by dx is the slope of this line. I can find it as tan theta and multiply that by dx, and I would get the value of dz. So, this is a special case where the slope of this is constant, it is a straight line, and it does not change in the y direction. So, I could find out this value in this form. But the more general case is where I have this slope even in one direction as changing. So, in this particular structure which is drawn over here, what we see is that this is, for example, the x axis, this is the y axis, any line parallel to this over here is the z axis. Over here also, one of the things we see is as we go along the x direction, if I go here or here or here, as I go along the x direction, the value of z changes. So, z varies when x varies. So, mathematically we say z is a function of x. But what we see is if I go along the y direction, for example, if I go here, the value of z is not changing here. If I go here, the value of z is not changing. So, for any given value of x, if I go along the y direction, in this particular graph, the plot which is shown here, the value of z does not change. So, z is not a function of y, but z is a function only of x. So, here again it is a function of only one variable, which is x. So, in a similar fashion to what we wrote earlier, if I go small distances along the axis, I can say that dz is dz by dx into dx. But in this case, what we see is that because the slope along the x axis itself is changing. So, for example, the slope here at this location is different from the slope here. So, I cannot write this for large distances. So, if I was to use this, for example, between x is equal to 0, between this point and this point, and use some value of dz by dx at say the center, the answer I would get in this case would be wrong. So, I can use this only when dx is a small distance. So, then if I want to know, for example, what is the height over here, what I can do is that height is what I would call as delta z. So, I would get delta z by integrating integral of dz, which is integral of dz by dx. dz by dx is the slope. I integrate the slope and multiply by the distance. So, what this is equivalent to doing is to finding out the slope over here in this first portion and multiplying that by this. So, if I do that, I get this distance, then integrating dz by dx, take this slope and multiply by this distance, which then gives me essentially this portion, and then finding out this slope, multiplying it by this distance, which gives me this, and then finding out this slope, multiplying by this distance, which gives me this portion, and then finding the slope here, multiplying it by this distance, which gives me this, and if I sum up this plus this plus this plus this plus this, that gives me the change in z between the final point here, some point 2, and the initial point here, which is some point 1. So, by integrating, what we are doing over here is essentially summing up all of these, and by using this dz, what we are saying is we will take small bits of this and then find out whatever is the value here and then sum them up. So, that is essentially what we are doing when we are integrating a small differential element dx. So, this is essentially what we are doing over here. So, in this kind of a curve, because nothing is changing along the y direction, it does not matter whether I do this on this line or I can do this, for example, on this line over here. The z value does not depend on which line I choose. I can do it on that line or I can choose to do it on this line also, because what we see is that the z value is only varying as I go from x equal to 0 to some other value. So, if I wanted the value over here, it is equal to the value over here and here and here and here. So, I could find the value at any of the points on this line, and in order to find out the value over here, I can do it from z equal to 0 and come here, from x is equal to 0 to here, or I can also, if I knew the value at x equal to 5, I can also come down from x is equal to 5 to here. So, it does not matter, I can find this value in many ways. And what I can also do is to choose to go to this point in sort of convoluted ways. So, for example, let us say I want to know what is the altitude at this point over here. So, this point over here corresponds to some x is equal to 4 and y equal to 3. I want to find out z when x is equal to 4 and y equal to 3. Over here what we see is it does not matter whether y is 3 or 2 or 1 or 0, because this is only a one, I mean it is a surface which has the slope changing only in one direction. The slope does not change when I go in the y direction. So, that is one thing which does not matter. But what I can also do is I can go along this line from some point here to some point here. So, I can do this integration from say this point A to this point C and then come downwards from C to this point B. If I knew the value at A and C, I can find out the value at point B. I do not need to go directly from A to B, I can go from A to C and then come down to B, because as you can see the height at this point is fixed. Whether I find the height here and add the difference between these 2 points, or I find out the difference between here and then subtract this, it really does not matter, because it is a fixed surface. Any point on the surface I can find out in any fashion. So, these are all things which can be plotted on this graph, and they would be essentially what we would call as state functions or properties. So, the height at any point is a property at that point. So, that is something which we see. In contrast, even in the previous graph, what I can see is, let us say I want to know the height at this point. It is easy for me to do. I know the slope, I multiply by the x distance and I can get this height by using this formula. Here the slope is constant, so I can do this over longer distances without necessarily having to integrate, because if I did integrate this, which is what I should correctly do, delta z is essentially integral of dz, that is integral of dz by dx into dx from say some point 1 to any point 2 which I want. Delta z is expanded as z2 minus z1. This dz by dx is a constant, we can see that. So, over here at this point dz is 20 over here, because the top of the z plane is 20. So, at the farthest point over here, at this point, at this location, this height is 20 and this length is 10. So, dz by dx is 20 by 10, which is 2. I can confirm that the slope is constant by taking other points. For example, let me take this point. Over here, I see the x is 4 and corresponding to x is 4, I see that lies over here, which is z as 8. So, dz by dx is 8 by 4, which is 2. So, this is essentially a constant. Since it is a constant and I know the value of the constant also, I can take it out of the integral. So, that is 2 and the integral of dx is delta x. So, I get 2 times delta x. So, the difference is just 2 times whatever is the distance on the x axis and nothing is changing on the y axis. So, what I can see is in the same way in which you saw previously, if I wanted to know what is the height over here, okay. So, along the x axis this is 1, 2, 3, 4, 5, 6. If I wanted to know what is the height there, I know it is 2 times the distance I go. So, the height here compared to x equal to 0 is 2 into 6, which is 12. The height here compared to this point is 2 into 2 blocks, which is 4. The height here compared to this point is also 2 into 2 blocks, which is 4. So, I can find the height here in terms of any of the points ahead of it or before it. So, that is easy to find out, and whether I find it with respect, so at this point A, whether I find with respect to B or with some other point here or here or here, I will get the same answer finally if I consider each point's elevation with respect to the ground. So, if I come to this point A along this path or along this path, or if I go like this and come here, or if I go somewhere like this and come to A, anytime I reach this point A, I am at a height of 1, 2, 3, 4, 5 into 2, which is 10 units above the ground. So, that is the important point here. So, I have a defined point on this. When I come to this point, I know what the height is. It is 10 units above the ground. It does not matter whether I go directly from the ground on this slope or I go some way like this and come here, or whether I come from here or come from here. Whenever I reach this point, I have the same height above the ground. So, this kind of thing is what we would call as a point function or a property. Now, I can ask a different question. How much distance did I travel to reach this point A? Starting from, let us say, the origin. Let us say starting from this point. So, what you see is, if I now went along this path, I travelled quite a long distance. If I went along this path, went like this and climbed up, I travelled some other distance. If I go over here and came down to point A, I travel this distance. So, we see that the distance I travel is different each time I come to this point A, depending on which path I take. So, that is an example of what will be called as a path function, because it depends on how much which path I travelled by. So, similarly, for example, let us say this represents some map. I am going in a car and I want to travel to this point. How much petrol will I use? So, assuming that my car's characteristics are constant and so on, I know that if I travel a longer distance, my car consumes more petrol. If I go from here to some other city and then come back here, I am at the same point where I started, but obviously I have spent a lot of petrol in coming back. So, it does not matter where I am, how much petrol I use depends on what distance I travelled or which path I followed. So, if I was to travel by this path, I would use a smaller amount of petrol compared to if I, for example, travel like this and then came like this and came like this. So, that is what we see. So, those kind of functions which depend on what path we take are essentially called as path functions. Now, these are essentially graphs where the slope is only in one direction. It does not have any slope in this direction. So, if I am on this point, if I am moving with respect to y, z does not change. So, this is an example of that kind of a case. This is also an example of that kind of a case. If I go along this line, my y is changing, but z is not changing. So, for a given x, if I move along y, z does not change. So, these are cases where z is a function of only one variable. A more general case would be where z changes. If I go along x, z also changes if I go along y. So, for example, let me take this point here. The z value on this point is 0. I have moved along the x, the z value here is 0. If I now go inwards along the y direction, the z value is changing. Now, if I take some point here, the z value is 0. If I move along the x direction, the value of z is changing. This is going up. And if I take this point here, if I moved only along the x direction for 5 units, the z value is 0. But if I moved along x direction for 5 units and along y direction for 1 unit, then I see that my value over here is corresponding to this line. So, this is along z, this is 5, 10, I am just writing out whatever values are here, 15, 20 and 25. So, if I moved 5 units along x direction, then value of z is 0. If I moved 5 units along x direction and 1 unit along y direction, my value of z is 5. If I moved 5 units along x direction, 2 units along y direction, I have 10. If I move 5 units, this is 5, this is 3, this is 1. If I move 5 units along y direction and 5 units along x direction, then I would reach essentially the point. So, 5 units along x and 5 units along y will get me to this point over here on the plane below. On that point, the altitude is 25. So, I see here that the altitude z varies if I go along x direction. It also varies if I go along y direction. So, I see that z is a function of x and y, which is to say that z varies if I go along x, it also varies if I go along y. So, in these cases, if I want to know or if I want to change in z, I need to account for changes in z along both the directions. So, what we would say is that dz is the change in z with respect to x when y is equal to constant multiplied by dx. This is similar to what we had earlier, and we have plus the change in z with respect to y when x is kept constant times dy. So, essentially what we are saying is, if I want to know, let us say the altitude at this point from the ground, what I can do is go along the x direction and find out the change in z. So, I go from here along this line, for example, find out the change in z. This term gives me that change. Then I go along the y direction and then find out the change in z. Add up these two changes, I will get the total change in z. So, over here d indicates the total change. This dou, we call it as dou z by dou x. This represents the partial change, which essentially says the change in z only when I am going along x keeping y constant. This bottom is to say that y is constant. So, this is the change by this line, change given with respect to going along x, but keeping y constant. So, if I was to go from here to here directly, or say from here to here directly, when I am going here, x is also changing, y is also changing. So, in order to find that, what I am saying is, instead of doing this, let me go along x, keep y constant, find the change, and then go along y, keeping x constant, and find the change. I could also do this first and then do this. So, which is to say, I can also go like this. I can go here, keeping x constant. I am going along x is equal to 0. I am going along this y axis, which is x is equal to 0. I am keeping x constant and going along y axis, changing y. I can find out the change, and then I can go to this term, which is I can go along the x axis, find out the change in z, keeping y constant, and whether I do this and this or this and this, I get to the same point. Therefore, I can find out the change in z with respect to the ground. Of course, I can also do the same thing to find the change in z between any 2 points. So, if I wanted to know what is the height difference between this point and this point, I can do this considering this as my initial point and this as my final point. So, but this, what we saw here is, this will, like in the previous cases, this will only work if the slope is constant in the whole region I am going. So, if my slope is constant along this, then I go here, then I can use this, but a more general form is, if I want to know the change in z, I need to integrate, like in the previous case. So, I need to integrate So, this will give me the actual change. So, if I want to go, for example, from some point here to some point here, and let's say the slopes are changing as I go along x also and along y also, then what I can do is I can integrate this. If I know the equation of this curve, I can find out, put an expression directly, or I can make it into small bits like this, and then say for the first portion this is the change, then for the second portion I find the change and multiply by dx, find the slope, for the third portion I find the slope, multiply by dx, and so on. Then in this direction I can get here, and then so what I can do is I can go along this line. This line I split it as dou z by dou x into this change dx, then this dx, then this dx, the local dou z by dou x into each dx, and then come here and then do the same thing along the y direction. Find out dou z by dou y, height difference with respect to y for this dy, add it to what was the change for this dy, and add it to change for this dy, and then I would get this value. Instead of going like this, what I can also do is I can go here and then go here. It will give me the same value. What I can also do is, instead of taking all of these summations first and all of these summations later, I can take intermediately however I want. So, what I can do is I can say I will first go here, then take along y, then take along x again, then take along y, again along x, again along y, and again along x, and reach here. So, I can take this dou z by dou x into this dx, plus dou z by dou y into this dy, plus dou z by dou x into this dx, plus dou z by dou y into that dy, and so on, and do this, and I reach the same point here, and I will still get the same change with respect to the ground, if I am finding out with respect to the ground. So, finding out, for example, between point 1 and some point 2, where point 1 represents the ground and point 2 represents this. So, I can also do this and I will get the same answer. So, what we see is, so more generally we have functions, some z which is a function of two variables, and dz if it is a function of two variables and this z represents some point on this map, then dz can be written in this fashion. Now again, if I was to look at the distance travelled rather than the height at some point, then the distance I travel to go from point 1 to 2 is different depending on how I go. So if I go like this, then I get 1, 2, 3, 4, 5, 6, 7 units of distance. If I go like this, 7 units along x and y. If I go like this, I get 1, 2, 3, 4, 5, 6, 7. But I can also go in some other fashion. So for example, I can go like this. I could also have gone like this. Nothing stops me if I am doing that. And then I see that between here and here, if I go in this fashion, I travel a much longer distance. So again, what we see is, if I am just looking for the height, that is a point, height at a point on this is fixed with respect to any other point, and that can be got by some formula like this. But if I want the distance, this does not give me the distance, because the distance travelled depends on how exactly I went there. So that is an example of a path function, and we cannot write those in this form, because this only takes into account change differences between x and y from some reference point, whereas the distance is not dependent on the difference, direct difference alone. So the difference in x here between here and here is say 3, but if I went 3 times along this, if I went here, here and here, the distance would have been 3 into 3, which is 9, but the difference in these 2 points is still only 3. So I do not get the distance or anything else which depends on the path in some form like this. So that's essentially what we see.